Hey there, future electrical engineers and curious minds. Ever wondered how electricity magically appears in your home, ready to power your latest gadget or illuminate your late-night study sessions? Well, get ready to unravel the mystery as we delve into the captivating world of electric power distribution. Buckle up, because we're about to embark on an electrifying journey. Today, we're going to be focusing on a crucial element of this system: polyphase circuits. Imagine a team of superheroes, each possessing unique powers, working together to deliver electricity safely and efficiently. That's polyphase in a nutshell. We'll also be exploring the heart of it all, AC generators, and how they generate the electrical power that keeps our modern lives humming. From the simple elegance of single-phase systems to the robust efficiency of their three-phase counterparts, we'll break down complex concepts into bite-sized pieces. So whether you're a seasoned pro or just starting to explore the fascinating world of electrical engineering, grab your thinking caps and let's get this current flowing. Imagine you're at a concert and the music is being produced by a single speaker. It might sound decent, but something feels lacking, right? Now, picture a full band with multiple instruments playing in harmony, creating a richer, more dynamic sound. That's the magic of polyphase circuits. In the realm of electrical engineering, polyphase circuits are like that well-coordinated band. Instead of a single current, they utilize multiple currents, each slightly out of sync with the others, to deliver power more efficiently. Think of it as a team of electrical horses pulling a carriage. They can carry a heavier load together than a single horse could manage alone. These multiple currents, known as phases, are generated simultaneously by AC generators. Each phase is like a separate wave, oscillating at the same frequency but shifted in time. Polyphase circuits are the backbone of our modern power grid, efficiently transmitting electricity over long distances and powering everything from industrial machinery to your humble refrigerator. Let's talk about the rock stars of the electrical world, AC generators. These ingenious devices are the beating heart of our power systems, tirelessly churning out the alternating current, AC, that keeps our lights on and our smartphones charged. Without them, we'd be plunged back into the dark ages, fumbling around with candles and carrier pigeons. But how do these electrical marvels actually work? Picture a spinning bicycle wheel with magnets attached to its rim. As the wheel rotates, so do the magnets, creating a changing magnetic field. Now imagine a coil of wire placed near this spinning wheel. As the magnetic field changes, it induces a voltage in the coil, causing an electric current to flow. By rotating a magnetic field within a stationary set of conductors, they convert mechanical energy into electrical energy. These generators come in all shapes and sizes, from the massive turbines in power plants to the portable generators you might use for camping or during power outages. Let's start our exploration of AC generators with the simplest form, the single-phase generator. As the name suggests, this type of generator produces a single alternating current waveform, a single sine wave oscillating back and forth. It's like the solo artist of the generator world, delivering a simple yet effective performance. Imagine a lone surfer riding a wave. The wave rises and falls in a smooth rhythmic pattern. That's your single-phase AC waveform. Single-phase generators are often used in residential applications, powering homes and small businesses. They're like the reliable workhorse of the power grid, providing a steady stream of electricity for our everyday needs. While single-phase systems are perfectly adequate for many applications, they do have their limitations. If single-phase generators are the solo artists, then three-phase generators are the rock bands of the electrical world. Instead of a single waveform, they generate three separate AC waveforms, each shifted by 120 degrees from the others. It's like having three synchronized surfers riding waves, each cresting at a slightly different time. This phase shift is the secret source of three-phase power. It creates a smoother, more consistent flow of electricity, much like a well-rehearsed band produces a richer, more dynamic sound. Instead of the pulsating power delivery of single-phase, three-phase systems, provide a constant and balanced flow, reducing vibrations and increasing efficiency. The three phases work together, balancing each other out and ensuring a smooth, uninterrupted flow of electricity. This makes them ideal for high-power applications, like industrial motors, large buildings, and of course, powering entire cities. Now, let's clear up a potential point of confusion: single-phase, three-wire systems. Don't let the name fool you. These systems are still considered single-phase, even though they use three wires. In a single-phase, three-wire system, two of the wires carry the hot AC voltage, while the third wire serves as a neutral. The voltage between each hot wire and the neutral is the standard single-phase voltage, for example, 120 volts in the US, while the voltage between the two hot wires is double that, for example, 240 volts. Think of it like a power cord with an extra prong. That third prong, the ground wire, is there for safety, providing a path for stray currents to flow safely to the earth in case of a fault. These systems are commonly used in residential settings because they allow for both 120 volts and 240 volts appliances to be powered from the same supply. So, while your lights might be humming along on 120 volts, your electric oven can crank up the heat with a full 240 volts. When it comes to connecting three-phase sources, there are two main configurations, Y and delta. Let's start with the Y connection, named after its resemblance to the letter Y. Picture a peace sign. That's the basic shape of a Y connection, with three branches converging at a central point. In a Y connection, each of the three phases is connected to a common point called the neutral. The voltage across any one phase and the neutral is called the phase voltage, while the voltage between any two phases is called the line voltage. In a Y connection, the line voltage is always 3, approximately 1.73 times greater than the phase voltage. Y connections are commonly used in applications where a neutral connection is required, such as in 4-wire, 3-phase systems used in commercial and industrial settings. They're also often used for supplying single-phase loads at a lower voltage. Now let's switch gears and explore the delta connection, named after its resemblance to the Greek letter delta. Delta. Imagine a triangle. That's the basic shape of a delta connection, with the three phases connected in a closed loop. Unlike the Y connection, there's no central neutral point in a delta connection. Instead, the phases are connected end-to-end, forming a continuous loop. In a delta connection, the line voltage is equal to the phase voltage. However, the line current is 3 times greater than the phase current. Delta connections are typically used in applications where high current levels are required, such as in industrial motors and large heating loads. They're also used in some power distribution systems, particularly in situations where a neutral connection is not needed. Understanding the relationship between voltage and current in YE and delta connections is crucial for analyzing and designing three-phase systems. In a Y connection, the line voltage is 3 times the phase voltage, while the line current is equal to the phase current. Think of it like this: the voltage gets a boost while the current stays the same. On the other hand, in a delta connection, the line voltage is equal to the phase voltage, but the line current is 3 times the phase current. These relationships are essential for understanding how power is distributed and utilized in three-phase systems. They're like the fundamental equations of three-phase power, allowing us to calculate and predict the behavior of these systems with precision. In the world of AC circuits, timing is everything. Just like a well-coordinated dance troupe, the phases of a polyphase system must be perfectly synchronized to ensure smooth and efficient operation. When phases get out of sync, it can lead to a whole host of problems, like unbalanced loads, reduced efficiency, and even equipment damage. Imagine a three-legged race where one runner is slightly out of step with the others. It's going to be a bumpy ride, right? Similarly, when the phases of a three-phase system are unbalanced, it can create uneven loads, causing one phase to work harder than the others. This can lead to overheating, increased energy consumption, and a shorter lifespan for your electrical equipment. Phase imbalances can occur for various reasons, such as unevenly distributed loads, faulty equipment, or even something as simple as a loose connection. Regular inspections, proper load distribution, and timely repairs can help prevent phase imbalances and keep your electrical system running smoothly. As we've discovered on our electrifying journey, polyphase circuits are the unsung heroes of modern power distribution, quietly and efficiently delivering the electricity that fuels our lives. From the simple elegance of single-phase systems to the robust power of their three-phase counterparts, these systems are the backbone of our electrical grid, powering everything from our homes and businesses to sprawling industrial complexes. As we move towards a more electrified future, with renewable energy sources like solar and wind power taking center stage, the importance of polyphase systems will only continue to grow. Their ability to efficiently transmit large amounts of power over long distances makes them essential for integrating these distributed energy sources into the grid. So, the next time you flip on a light switch, power up your computer, or marvel at the intricate workings of an industrial machine, take a moment to appreciate the silent symphony of polyphase circuits humming along, making it all possible. It's a testament to the ingenuity of electrical engineering and a glimpse into the electrifying future that awaits us. Picture this: 3 power lines converging at a single point, forming a Y-shaped arrangement. That, my friends, is the essence of a Y connection, also known as the star configuration. In this setup, each line connects to a common point, often grounded for safety. The Y connection is like the Swiss Army knife of power distribution, found everywhere from homes to industrial behemoths. Why? Because it's versatile, allowing for both single-phase and 3-phase power. Each line and the neutral form a single-phase circuit, while all 3 lines together pack a 3-phase punch. This flexibility is a major win, making the Y connection a star player in the power grid. Now let's talk voltage. In a Y connection we have 2 flavors, line voltage and phase voltage. Line voltage measures the voltage between any 2 lines. Phase voltage measures the voltage between a line and the neutral point, the relationship between them. Line voltage is always the square root of 3 times larger than the phase voltage. The Y connection can handle unbalanced loads like a pro, distributing the load without breaking a sweat. This makes it a robust choice for systems where loads can be unpredictable. Hold on tight because things are about to get interesting. We're diving into the world of delta connections, also known as mesh configurations. Unlike the WI connection with its central meeting point, the delta connection is all about closed loops. Picture 3 power lines forming a triangle, their ends connected in a continuous loop. This closed loop is where the delta connection gets its mojo. It's like a closed circuit of power, constantly flowing between the lines. But here's the catch: there's no neutral point in a delta connection. It's all about the 3 phases working together in perfect harmony. In a delta connection, line voltage and phase voltage are equal. The voltage across any 2 lines is the same as the voltage across any 1 phase. Delta connections thrive on balance. That's why delta connections are typically used in systems with predictable, balanced loads. Let's talk power, people. Specifically 3-phase power, the unsung hero of modern electrification. Imagine a single-phase system like a lone wolf trying to pull a heavy sled. It works, but it's inefficient and prone to jerky movements. Now picture a 3-phase system, like a team of huskies pulling in perfect synchronization. The load is distributed evenly, the ride is smooth, and the efficiency is off the charts. That's the beauty of 3-phase power. It delivers a constant, pulsating flow of energy, unlike the fluctuating nature of single-phase power. This means less vibration, higher efficiency, and the ability to transmit more power with less conductor material. 3-phase power is also the muscle behind those big industrial motors that keep factories running. Without 3-phase power, our industrial world would grind to a halt. Now that we've got a handle on Y and delta configurations, let's see what happens when we connect them. First up, the YY system, the vanilla ice cream of 3-phase setups. It's simple, reliable, and gets the job done. In a YY system, both the source and the load are wired in a Y configuration. This symmetry makes for a balanced system, as long as the load is also balanced. One of the big advantages of the YY system is its versatility. It can handle both balanced and unbalanced loads without breaking a sweat. This makes it a popular choice for applications where load variations are expected, such as residential and commercial buildings. However, the YY system isn't known for its high voltage capabilities. Get ready for a plot twist. We're about to explore the Y-delta system, a 3-phase configuration that's all about transformation and balance. Imagine a power system that can step down voltage while handling unbalanced loads like a champ. That's the Y-delta system in a nutshell. In this setup, the source is wired in a Y configuration, while the load rocks a delta connection. This configuration is like a voltage transformer, stepping down the line voltage by a factor of the square root of 3 at the load. This is particularly useful when you need to power lower voltage equipment from a higher voltage source. The Y connection on the source side acts like a buffer, absorbing any imbalances and preventing them from wreaking havoc on the delta load. This combination of voltage transformation and load balancing makes the Y-delta system a popular choice for industrial applications. It's like having the best of both worlds, all in one electrifying package. Hold on to your hats because we're entering the realm of heavy hitters. The delta-delta system is the workhorse of three-phase configurations, known for its robustness and ability to handle high-power applications without breaking a sweat. In this setup, both the source and the load are wired in a delta configuration. It's like a closed loop of power, flowing seamlessly from the source to the load. This configuration is all about efficiency and power transfer. One of the key advantages of the delta-delta system is its ability to handle high currents. Since the line current is split between two phases, the current flowing through each winding is reduced, leading to lower losses and greater efficiency. This makes it ideal for applications where high power is required, such as large motors, industrial heating, and heavy machinery. However, the delta-delta system is not as forgiving as the YY or Y-delta configurations when it comes to unbalanced loads. Therefore, it's crucial to ensure balanced loads when using a delta-delta system. Ever wondered how electricity travels those long distances from power plants to our homes? The answer: high voltage transmission lines. And guess what plays a crucial role in this electrifying journey? You guessed it, the delta-Y system. This configuration is like the voltage booster of the three-phase world. It steps up the voltage at the source, delta connection, and then steps it down at the load, Y connection, making it ideal for long-distance transmission. The delta connection at the source allows for higher phase currents, which in turn results in a higher line voltage. This higher voltage is then transmitted over long distances with minimal losses. At the load end, the Y connection steps down the voltage to a level suitable for distribution and consumption. The delta-Y system isn't just about boosting voltage, it also provides a convenient neutral point at the load end, thanks to the Y connection. This neutral point is essential for grounding and for providing a return path for single-phase loads. Now that we've explored the different configurations, let's talk about the real star of the show: power. In the world of electricity, power is king, and three-phase systems reign supreme when it comes to efficient power delivery. In a three-phase system, power isn't just about voltage and current, it's about the relationship between them. This relationship, known as the power factor, determines how effectively the electrical energy is being used. A high power factor means efficient power transfer, while a low power factor indicates wasted energy. Why is this important? Well, a low power factor can lead to higher energy bills, increased losses in transmission lines, and even equipment overheating. Three-phase systems are inherently more efficient at delivering power than single-phase systems. This means less vibration, less stress on equipment, and ultimately, higher efficiency. Power is nothing without control, and in the world of electricity, watt meters are the instruments of choice for measuring and monitoring the flow of energy. These ingenious devices provide insights into the power consumption of circuits, helping us optimize efficiency and troubleshoot problems. Think of a watt meter as a power detective, meticulously analyzing the voltage and current waveforms to determine the true power being consumed. Unlike a simple voltmeter or ammeter, which only measure voltage or current individually, a watt meter takes into account the phase relationship between them. This is crucial because, as we learned earlier, power factor plays a significant role in power consumption. Watt meters come in various shapes and sizes, from traditional analog meters to sophisticated digital meters, with advanced features and data logging capabilities. Regardless of their form factor, they all share the same goal: to accurately measure power. With the increasing emphasis on energy efficiency, watt meters are becoming indispensable tools for a sustainable future. Measuring power in a three-phase system might seem daunting, but fear not. We have 3 trusty methods at our disposal, each employing a different number of watt meters. It's like choosing the right tool for the job, depending on the complexity of the circuit and the information required. For balanced loads, The 1 watt-meter method is our go-to hero. By connecting a single watt-meter to one phase and the neutral, we can extrapolate the total power consumed by the entire 3-phase load. When dealing with unbalanced loads, the 2 watt-meter method steps up to the plate. By connecting 2 watt-meters to 2 of the phases, we can accurately determine the total power consumed, even if the loads are unevenly distributed. For the most comprehensive analysis, the 3 watt-meter method takes the crown. By connecting a watt-meter to each phase, we can obtain individual power readings for each phase, providing a detailed picture of the power distribution within the system. It's like having a magnifying glass, allowing us to zoom in on each phase's power consumption. Congratulations! You've now journeyed through the electrifying world of polyphase circuits. From Y and delta configurations to power calculations and measurement techniques, we've covered it all. But this is just the beginning. The world of electrical engineering is vast and ever-evolving, with endless opportunities for learning, innovation, and pushing the boundaries of what's possible. Whether you're a student, a hobbyist, or a seasoned professional, there's always something new to discover in the realm of circuits and power. If you found this video helpful, don't forget to give it a thumbs up. Subscribe to our channel for more electrifying content, and share it with your friends.